to introduce you to my new 3D printed or largely 3D printed rose engine. On the top of the carriage we have a standard Rutland's chuck, which is connected to by a thread cut on my lathe, a linear bearing which I happen to have at the front of the carriage, and at the back we have just some standard bearings in a 3D printed housing. The body of the headstock is all 3D printed, and if you go around the other side, two bolts there, I can take that side off so that I can tackle the nuts which move the engine up and down to tighten the belt. These are the main 3D printed components of the headstock. The two long thin bits with the gaps in are for the main uprights connected to the bearing on which it sits. The two H pieces join those two together, as you will see in the next picture. Here is the partially completed headstock frame. One more upright to add. Here is the fully completed headstock frame. It is held together by friction, and the main threaded rod at the bottom on which the bearings sit, and a threaded rod at the top which pulls it all tight. This is the view of the headstock with it turned upside down. This is one of the two side panels prepared to have threaded inserts which will take the bolts from the other side panel. The brake mechanism here, which I'll explain a bit later, these pillars are made of wood because they needed to be quite rigid, as is the cross beam, as is the next one. The follower is a bearing follower that's been 3D printed and is held in place by tightening these nuts, as is the brake, which is held in place by tightening these nuts. The rosette is 3D printed. This is a mechanism which loosens off the rosette for phasing. I tightened it up again. The base came from a 3D printer. In fact, it was getting rid of the 3D printer that made me start this process. Inside there is a power supply which supplies, there's a 48 volt output there which I'm not using. On this side we have one 48 output and two 12 volt outputs, and a potentiometer to control the speed of the cutter motor. The cutter motor operates at 48 volts and came from a CNC machine that I upgraded. The XY table came from the 3D printer, as did the small stepper motors, and this has allowed me to control the carriage by stepper motors rather than by hand, which means I can move it forward, backwards, the X and Y, and actually the Z, using this control here, which is a small combination that AI helped me develop and based on an Arduino. This next one is also based on an Arduino with a SaneSmart keypad shield. That controls the power to the laser, which I will talk to you about later. This is another Arduino based touchscreen which controls the headstock motor. It's a variation of the buttons that I had on my previous machines, but I thought it'd be nice to have a keypad shield. Sorry, an LCD. There's a light there to help shed light on the work. The motor is housed in a 3D printed housing based on some MDF to elevate it. The rest of the woodwork here is woodwork and is used. I used wood because I wanted some rigidity in this area. The tailstock will unbolt from the whole process, and then I can turn it through 90 degrees to work on the side of pieces, which is, as far as I can tell, not something anybody else has ever done. Here it is in its configuration to work on the side of pieces. I'll just demonstrate how the XY table works. Don't know if you can see this. No. I will turn the lights off. Still too bright, you'll have to take my word for it.
The travel on the XY table is determined by pushing and turning the button on this device.
The x-axis can move 10mm at a time. If I want, I can reduce that to 1mm. Or even 0.1mm. Which is really quite useful when you're working with the rotary engraver. I'll show you the y-axis moving. Again, that can move 10mm, 1mm or 0.1mm. There's the motor going. And here is the headstock moving. These are the controls for the headstock motor. I don't know if you'll be able to read them, but these are the control for the laser. And finally, this is the control for the XY table. For phasing, I tighten the brake on the rosette. Loosen off the barrel here, and then the motor can turn by as much as I need. let's say, leaving the rosette firmly in place. So I've set it to divide a circle into 24 visions. So if I press move, the work will move 1/24 of a circle, and the rosette stays where it is. Tighten up that, release the brake, and any further work can be done at 1/24 phasing. The control will allow me to divide a circle up into anything from 1 to 36 divisions, and angles are increased by a degree at a time. A little drawer here that houses some of the electronics and the wiring for the laser when that's fitted. Bit awkward to get to when the lathe is in this configuration, but when it's in its normal configuration, it's quite a useful place. Here it is with the laser installed. The laser is installed on a Z-axis, which is a bit of overkill really, because once it's centered I probably won't need to change that again, but I did it because I had a Z-axis and I thought it might be fun. The laser is now just a little bit further away from its optimal distance, so I will close it in. That's probably the optimal distance. Have a eye protection shield on a flexible mounting. So I will turn that on and set the laser to 50% power. Press arm, and you may be able to see beyond the screen a pattern developing. One of the disadvantages of having the protection on the laser itself is I can't really see what's going on.
I realise now that you couldn't see an awful lot in the section that I planned with the eye protection in the way, so I have temporarily removed it in part so that you can see the laser working and also the effect of the phasing. So there's what we've etched so far, and we will now use the phasing mechanism to try and retrieve a proper phase effect. Hopefully now this will work.
Right, let's see what we've got. Hooray! The phasing has actually worked.